That's distortion in amplifier circuits. All right. Now, what do you mean by distortion? Okay. To explain the concept of distortion, let me take a simple example. Okay. Say, for example, this is our power amplifier circuit, PA. Okay. So to this power amplifier circuit, let us give input signal. Assume that your input is a proper sinusoidal signal. In the sense, it's a pure sinusoidal signal. So this is P in. Okay. And let's say this is okay. Instead of P in, this should have been V in, right? Yeah. Input is sinusoidal and output. Okay. Now, two ways of getting the output. The first way of getting the output is to get faithful amplification. The first way of getting the output is faithful amplification, in the sense, if your input is a sinusoidal signal and if your output is also sinusoidal, okay, if the output is also a pure sinusoidal signal, then we would say that the amplifier has, amplifier is successful in producing a faithful amplification. Okay, but this is very an ideal case. But in reality, you may not get faithful amplification all the times. Okay, let's say this input is sin omega t. Okay, so V in is equal to Vm into sin omega t. Okay, so your output V naught is equal to some V naught m sin omega t. So you can observe that in case of faithful amplification, if the source frequency is omega, the output frequency will also be omega. Okay, and if you look at the wave shape, your input wave is purely sinusoidal and your output is also purely sinusoidal. But in reality, this may not happen. In reality, okay, you may get the output may be of following type. Okay, you may get output of this kind. Okay, so this is your output. Okay, or you may also get the output of this kind. Okay, so this is also, say, V naught. Okay, and this is your T, okay, or omega T. All right, now if you compare the input, okay, input starts from 0 offset value. That means to say the input voltage is starting from 0 volt level. But if you see the first output, okay, you observe that the first output is not starting from origin. Instead, it is starting with some delay angle phi. Okay, so this is called as phase distortion. This is called as phase distortion. So that leads to improper amplification. So this you cannot call it as a faithful amplification, because the phase of input voltage is 0, but the phase of output voltage is some 5 degrees. Okay, that is called as phase distortion. Okay, and the signal is still sin omega t, in the sense if the source signal is having an angular frequency of omega, the output signal is also having an angular frequency of omega. Okay, now in the second case, if you observe, the phase is 0 degree. That means to say there is no phase distortion, but the equation of the sine signal is something like 2 omega t, in the sense the fundamental frequency of the input signal is omega, but the frequency of output signal is 2 omega. That means to say the output has frequency. Output has frequency, which is 2 times the fundamental frequency. Two times the fundamental frequency. Okay, this is called as frequency distortion. This is called as frequency distortion. Okay, now the phase distortion. Okay, phase distortion is not a very important phenomenon in audio amplifier. Okay, AF means audio frequency amplifiers. Okay. Not so important. Okay, why? Because the phase distortion cannot be detected by human ears. Okay, since human ears cannot detect the phase distortion, you can neglect the effect of phase distortion. On the other hand, this frequency distortion is very, very important. That's because the variation of frequency, in short F, causes amplitude distortion. Okay, so that's the reason the second part is very, very important. Okay, all right. Now let us look at the amplitude distortion. Okay, now in our previous classes we used to write an expression for collector current, okay, IC, as beta times IB. Okay, beta times IB. In the sense, we used to always assume that the response between base current and collector current is a linear one. That means to say, we used to assume that the transistor is a linear device. But in reality, transistor is not a linear device. Instead, transistor is a non-linear device. Now, due to this non-linearity, what happens is that the waveform of the output voltage differs from that of the input signal. All right, let me repeat. Due to the non-linearity, the waveform of the output voltage differs from that of the input signal. Now, such a distortion is called as non-linear distortion or amplitude distortion. Okay, so such a distortion is called as amplitude distortion or harmonic distortion or non-linear distortion. So it is non-linear distortion or amplitude distortion or harmonic distortion. Okay, synonyms. Okay, so that's the effect. Okay, so let me quickly recap. If the amplifier output follows the input, then it is called as faithful amplification. If the amplifier output doesn't follow the input, then it is called as non-faithful amplification. Okay, now in case of non-faithful amplification, there can be two types. In one type, there can be distortion in phase, as shown in figure 1. Okay, as shown in figure 1. This is called as phase distortion. Or you may also have something known as frequency distortion. So this frequency distortion basically leads to amplitude distortion. Okay, now what causes the frequency distortion or the amplitude distortion? The nonlinearity of the transistor. So for all our, in our previous analysis, we had assumed that transistor is a linear device. That is, IC is proportional to IB. But in reality, the transistor is not a linear device. Instead, the transistor is a non-linear device. Okay. So this is IC and this is IB. So this is your ideal and this is your practical. Okay. So due to this non-linearity, the nonlinear distortion creeps in, which is also called as amplitude distortion or harmonic distortion. Okay. Now let us look at the harmonic distortion. Okay. Now, harmonic distortion can be due to the second order frequency component, or the third frequency component, or fourth frequency component. Okay, so let's say, okay, let me talk about harmonic distortion. Okay, let's say this is my fundamental frequency or fundamental component. Let's say this is fundamental component. Okay, whose description is sine omega t. Okay. Now, let's say the output is of this kind. Okay. Say this output is consisting of second order component. Okay. So this is called as second harmonic component. So how do you identify second harmonic component? You have to just observe the frequency. The frequency is 2 omega, where omega is the fundamental frequency, right? So 2 times the fundamental frequency, hence it is second order harmonic. And you can also have third order harmonic. The third order harmonic will have 3 times the fundamental frequency. Okay, the idea is when your fundamental component completes 1 cycle, the third order component completes 3 cycles, and the second order component completes 2 cycles. So that's the understanding of second order component and third order component. So third order harmonic. And the description of the third order harmonic is sine 3 omega t. Okay. Now, due to the presence of this second order and third order harmonic, the actual output waveform, okay, this is your V naught actual, will be something like this. Okay, so this is called as amplitude distortion. Okay, so the harmonics basically affects the wave shape of the actual output, and that is called as amplitude distortion. Okay, now out of several harmonic components, second order harmonic is very high. Okay, and third will be low, and fifth going to be like fourth, fifth, sixth, seventh going to be very, very small. Hence, normally in analysis, we consider second order harmonic. So second order harmonic is very high and hence dominates, whereas third order harmonic and higher order harmonics, third and higher order harmonics are not so significant. Not so significant. All right. Okay. Next. Okay. So based on this understanding, you can derive a small expression basically. Let's say B1. Okay, B1 is the amplitude of fundamental component. Let's say B1 is the amplitude of fundamental frequency component. In the sense, say this is B1. Okay. Then let's say B2 is the amplitude of second order frequency component. Say this is B2, and similarly, let's take this as B3. B3 is the amplitude of third order component. Okay. Likewise, you can go on. So in the end, let us define that Bn is the amplitude of nth order component. Okay. Then the nth harmonic distortion, okay, denoted by percentage Dn, okay, is equal to nth harmonic component divided by fundamental component into 100. Okay, so this is how we calculate the harmonic distortion. Okay, so for nth harmonic distortion, it is the ratio of amplitude of the nth order frequency component divided by the fundamental amplitude. Okay, so similarly, you can write for second order, or you can say second harmonic distortion. Second harmonic distortion. Okay, what is it going to be? Second means n is equal to 2. So percentage d2 is equal to, okay, b2, because n is 2, right? b2 divided by b1 into 100. Okay. Similarly, third harmonic distortion, you can write it as percentage d3 is equal to b3 by b1 into 100. All right. So this is how we calculate the harmonic distortion. Okay. So the total harmonic distortion, therefore, total harmonic distortion, in short, it is called as THD. Total harmonic distortion, in short, it is called as THD, which is equal to percentage D is equal to under root D2 square, D3 square, D4 square, so on, so forth. Into 100. Okay, so this is the formula for total harmonic distortion. Okay, you will have problems based on this. Okay, we will solve subsequently. Let us look at those problems. Okay, so but this is the formula for total harmonic distortion. Okay, any doubts so far?
No, sir.
No. Okay, all right. Now let us look at an expression for second order harmonic component. Okay, as I said in the beginning, out of so many harmonics, the second order harmonic component dominates, because the second order harmonic component will have the largest amplitude amongst the lot. Okay, so third and higher order harmonics are of less significance, because their amplitudes are not so dominating one. Okay, so that's the reason in our analysis we'll be looking at only a second order harmonic component. Okay, so the next subheading going to be second order harmonic distortion. It's very, very important. Second order harmonic distortion. Okay, so this particular analysis is being carried out on the basis of 3-point method. You will understand eventually what you mean by 3-point method. Okay, there is 5-point method also, but don't want. Okay, 3-point method is sufficient to understand what is the nature of second harmonic distortion. Okay, now in order to understand second order harmonic distortion, first let me propose the non-linearity of the device. Okay, so in harmonic distortion, okay, first of all, why the harmonic distortion comes into picture? The harmonic distortion comes into picture because of non-linearity of the device. Okay, so your transistor behavior is non-linear. Okay, so this is the actual behavior. If I were to show you the ideal behavior, so this is going to be the ideal behavior. Okay, so dotted one is ideal and the solid line is actual. Okay, so this is your IC and this is your IB. Okay, now let us define the expression for base current as IB is equal to IBM into cos omega t. Okay, now why I have taken cos omega t? Why didn't I take sin omega t? That is only on the basis of calculation. So if I take cosine function, you know, my mathematical analysis becomes simpler. Only for that sake I have considered cos omega t. Okay, it will not affect your calculation because cosine function is nothing but time displaced sinusoidal function. So mathematically no harm done. All right. So let me assume, for the sake of simplicity, the base current IB as IBM into cos omega t. Okay. Now, okay, this is, let's say, figure 1. Okay. Now, with respect to figure 1, okay, with respect to figure 1, you know, you no longer say that IC is proportional to IB, right? Because this is not a linear characteristic. This is a non-linear characteristic. Okay, the typical mathematical equation which is used to, you know, express the non-linearity of a transistor is something like this. So instead of writing IC is equal to beta times or gain times IB, we normally mention IC is equal to some gain G1 into IB, okay, plus some gain G2 into IB square. Okay, now the first term G1 into IB is your normal term, right? Because IC is equal to beta times IB, where beta is the current gain or gain. So IC is equal to G into IB. So it follows your ideal behavior. That means to say, in this non-linear shape, okay, there is some linear portion. So that linear portion is, you know, addressed by G1 into IB, and the non-linear portion is addressed by the second term G2 into IB square. Okay, so we'll take this as equation 2. Now let us substitute the base current in equation 2. So substitute substitute 1 into. Okay, so when you substitute equation 1 in equation 2, you would get IC is equal to G1 into IBM cos omega t plus G2 into, it is IB square, so it is IBM square cos square omega t, or this is equal to G1 IBM cos omega t plus cos square omega t. I can write it as 1 plus cos 2 omega t divided by 2. So what I will do, G2 IBM square, I'll keep it as it is. Okay. So in place of, you know, cos square omega t, let me write it in orange color. I'll write it as cos square omega t, I will write it as 1 plus cos 2 omega t divided by 2. Okay, divided by 2. Or you can further simplify. IC is equal to okay, G1 IBM cos omega t plus you multiply with the first term. So it is G2 IBM square divided by 2. So it is 1 by 2 G2 IBM square. Okay. Plus the third term, that is half G2 IBM square cos 2 omega t. Okay. So this cos 2 omega t is basically a second harmonic component. Okay, all right. Or let me write IC is equal to, okay. Now what I will do, okay, let me just highlight. This term, let me take some B1, and this term, okay, which is independent of frequency. So let me take it as B naught, and this term, okay, let me take it as some B2. Okay, and let me define. Okay. Let me define those terms. Let B1 is equal to G1 IBM is equal to amplitude of fundamental frequency. Okay. Okay. Similarly, B2 is equal to what is it? Half G2 IBM square amplitude of second harmonic component. Okay. And B naught. Okay, B naught. What is B naught? Half G2 into IBM square. So there is no cosine term associated with B naught. Hence, you can call it as, you know, DC value. So B naught simply says that it's a DC value. So therefore, you can write IC is equal to, okay, B naught plus B1 into cos omega t, the fundamental frequency, plus B2 into the second order frequency cos 2 omega t. And let's call it as equation 3. Okay, equation 3. Okay. Now what we will do is, now let us plot the actual current waveform. Okay, so this is how we plot the actual current waveform. Okay. Now you know that in case of power amplifiers, there exists a quiescent value of current, right? So let us say this is the quiescent value of current. Let us say this is the quiescent value of current, ICQ. Okay. This is called as DC bias value. isn't it? Bias value. Now, above and below this DC bias value, your collector waveform toggles, right? Since we are talking about a cosine waveform, so cosine waveform will have a maximum value at origin, right? So this is how I'm going to draw the graph. Okay, all right. Next, let me mark certain points over here. Let me mark, say, point 1. And then let me mark point 2. And then let me mark point 3. Okay. So this is your omega t axis. Now, point 1, corresponds to 0 value. Okay. Point 2 corresponds to pi by 2 interval, because in case of cosine function, cos 90 is 0. So at pi by 2 interval, the cosine waveform will have its 0 value. And this will be the pi interval. Okay. So 0, pi by 2, and pi. So since I have taken 3 points, point number 1, point number 2, and point number 3, this method is called as 3-point method. Okay. Now, this waveform is basically your collector waveform IC. Okay. All right. So this is my actual, okay, let me write it, figure 2. So this figure 2 depicts actual collector current scenario. So, this is comprising of the quiescent value as well as the AC value. Okay. Now, since this particular waveform, you see in the previous equation, okay, in the previous equation, we just considered IC is equal to some nonlinear equation, and nowhere we considered the quiescent value, right? Because but in transistors, there exists a quiescent value of current also. So by considering quiescent value of collector current, the total collector current, okay, let me write total AC collector current is given by capital I and small c. Okay, that is IC is equal to, okay, the quiescent value plus IC. Let's say this is equation 4, right? The previous was 3. So this, let us take equation 4. Now, substitute 3 in equation 4. Okay, so what do you get? You get total collector current IC is equal to ICQ plus V naught. Okay, so let me put it inside a bracket, plus V naught plus B1 fundamental frequency plus B2 second order frequency. Say equation 5. Okay, say equation 5, where the sum ICQ plus B naught is equal to total DC component. Total DC component. Okay. Now what we will do is, now let us try to apply the points. Okay. Now let us say, what is a point value at 1, point value at 2, and point value at 3. Okay. If you look at closely, at point 1, omega t is 0, but IC is equal to I maximum. So this is the maximum value, right? So at point 1, you have I maximum. Similarly, at point 3, you have I minimum. Okay. And at point 2, you have IC is equal to ICQ. Okay. So let us just write on. Let us say this is omega t and say this is IC. Okay. So at omega t is equal to 0, IC is equal to I max. Okay. So what we will do, this let us write it as that capital IC. Okay. So at omega t equal to 0, IC is equal to I max. Okay. So this is at point 1. And at point 2, omega t is pi by 2. And at pi by 2, IC is equal to ICQ. And at point 3, it is pi. And at point 3, the IC value is I minimum. Correct. At point 3, IC value is I minimum. Okay. Therefore, okay, you can start substituting these point values one by one. So let us just substitute first. At omega t equal to 0, okay, equation 5 becomes, means to say when you substitute omega t equal to 0 in equation 5 becomes, okay, what is the value at omega t equal to 0? What is the value of IC? IC value is I max. So we can write I max on the left hand side. I max is equal to ICQ plus B naught plus B1 into cos 0. Cos 0 is 1, so it is B1 plus B2 into cos 0. Again, cos 0 is also 1. Okay, so this is our equation 6. Similarly, at omega t equal to pi by 2, okay, at omega t equal to pi by 2, that is at point 2, in equation 5, okay, what we get at omega t equal to pi by 2, we get IC is equal to ICQ. So this is ICQ is equal to ICQ plus B naught. Okay. This B naught is not there. Okay, ICQ plus B naught, because that's independent of frequency. Okay, plus B1 cos 90. Cos 90 is 0, so therefore B1 term gets vanished. Okay, then B2 cos 180, because 2 into pi by 2 is cos pi. Cos pi is minus 1, so it is minus B2. Minus B2. Say equation 7. Okay. Now, if you simplify equation 7, what you get? ICQ gets cancelled. You get B naught is equal to B2. So you get one expression, right? B naught, which is equal to B2. And similarly, at omega t is equal to pi, in equation 5 gives I minimum, right? At omega t equal to pi, IC is equal to I minimum, and I minimum is equal to ICQ plus B naught. Okay, minus, because B1 into cos pi. Cos pi is minus 1, so it becomes minus B1. Okay, then that is cos 2 pi, so that's positive. So plus B2. Okay, so that's your equation 8. Okay. Now what you do is you perform, let's say for example, I max and I minimum. I max is equation 6 and I minimum is equation 8. So when you perform I max minus I minimum, what do you get? You get ICQ plus B naught minus B1 plus B2 minus I minimum. So it is minus ICQ minus B naught plus B1 minus B2. Okay, so ICQ cancels, B naught cancels. Okay, and what did I miss? Okay, this is I max is equal to ICQ plus B naught. Okay, this is plus B1. I'm so sorry. This is B1, right? Because equation 1. Yeah. So B2 gets cancelled, and you are left with I max minus I minimum is equal to 2B1, or the amplitude of fundamental frequency B1 is equal to max minus min value of collector current divided by 2. So that is your B1. Okay, you're getting the point, right? What is B naught? B naught is the DC value, which is equal to the amplitude of second order harmonic component, and B1 is the fundamental component. Okay, and B2 can also be found using an alternate way. So what we will do, perform say I max plus I minimum. You add the max and min equations. Okay, so when you add max and min equations, what you get is ICQ plus B naught plus B1 plus B2. Okay, plus I minimum. Okay, I minimum is equation 8, so it is ICQ plus B naught minus B1 plus B2. So minus B1 plus B1 gets cancelled. So I max plus I minimum, okay, you'll get it as 2 ICQ plus 2 B naught plus 2 B2. But B naught is equal to B2. Therefore, you get 2 ICQ plus 4 B2, right? Because you're substituting B naught as B2 itself. And therefore, you know, your B2 going to be max plus min minus the quiescent value divided by 4. Okay. So this is the expression for B2. Okay. So once you know what is B1, what is B2, and what is B naught, you know, you can find out the second order harmonic distortion. Therefore, second order harmonic distortion, let's say percentage D2 is equal to mod of B2 divided by B1 into 100. Okay, so this is the expression. All right, this is the expression. Okay, this is very, very important. Normally it comes for 8 to 10 marks. Okay, either derivation, or problems. Compulsorily it comes. Okay, so very, very important. So you need to understand the derivation, because if they ask, you know, problems, if you can by heart expression for B1, B2, B naught, that's fine. Okay, if you don't want to by heart, you know, this is how you can derive quickly, and then you can substitute in your problems. All right, so that's the expression for harmonic distortion. Okay. Now, there's a small derivation regarding, power output due to distortion. Okay, again, you can derive this, but this is not that significant. Okay, so what I will do, I'll just give you a ready-made equation, which is easily understood. So power output, okay, due to distortion, let us define it as PAC, right? Because in case of power amplifier, output is always AC power output. So PACD. Okay, so that is AC power output under distortion. PACD is equal to PAC, okay, into 1 plus T square. Okay, where uh, expression for T, right? So D is what basically under root D2 square, D3 square, D4 square, so on so forth. So if you square the both sides, you will get D square. Okay, so that's the value of D. And what is PAC? PAC is equal to fundamental power. Okay. Okay, power delivered by the fundamental component. I'll just write power output due to the fundamental component. Okay, so that can be written as, Im square by 2, or you can write it as Vm square divided by 2Rn. Okay, so this is PAC. So power output due to distortion is equal to power output without distortion into 1 plus D square. So that's the formula. Okay, so this formula you can logically remember. Okay, so fundamental power you need to multiply with the distortion. So this is the distortion factor. All right.